Good morning, ladies and gentlemen. Same sweatshirt. We shot 3 videos today. Okay, so do now a 1.2 kilogram rocket at rest shoots 0.075 kilograms of hot gases out the back. Woo-wee. If the rocket then goes about 100 meters per second, how fast are the hot gases going?
On your mark, get set, go.
So in the beginning we have the rocket. This is before, and our momentum is equal to 0. It's not moving, right? And then after, we have like this, right?
Yeah.
And the 1.2 kilogram rocket, so the mass of the rocket is 1.2 kilograms. And it shoots out, this many kilograms of the mass of the gas, 0.075 kilograms. Out the back, the rocket is then going 100 meters per second.
No, the gases are going, oh no. No,
Right.
the rocket is 100 meters per second, and the gases, we want to know what that is.
And the velocity of the gas.
So we've got to do the pyramid thing.
Yeah, don't forget. So we're going to call this the positive direction. This is the negative direction. Pyramid thing, okay? And what kind of we've only talked about one. This is an explosion. And we know that the momentum at the beginning is equal to 0.
Well,
And the momentum at the end is going to be the momentum of the rocket plus the momentum of the gas, right?
afterwards, prime.
After. Yeah, thank you. Oh, I keep forgetting that. That's important. And at the beginning, it's not moving, so I'm just going to go ahead and subtract.
Where's the answer going to be?
Oh, great question. So the answer is going to lie in
Here.
this one right here.
So we got to solve for that.
Yeah, so let me go ahead and just subtract off the momentum of the rocket. The momentum of the rocket is going to equal the momentum of the gas. And so this is going to be negative mass times of the rocket times the velocity of the rocket is going to equal. Now, do you still keep the primes on there, Mr. Boykin, at this point?
For the V.
Yeah. Oh, thank you. Okay. Oh, that makes sense because the velocity is changing. And then the mass of the gas times the velocity of the gas. And again, that's what we want. We'll divide by this. Now, notice how I am not plugging in numbers yet.
That's a good thing.
It's easy like this, right?
Yeah.
Okay, so I've got, give myself more room here this time.
Atta
Trying
girl.
to give myself too much room. The mass of the rocket was 1.2 kilograms times the velocity of the rocket was 100 meters per second. Okay.
Divided by the mass of the gases,
Divided by the mass of the gas, which was
0.075.
Yes, 0.075 kilograms. Okay, let's do this. So I've got negative 1.2 times 100 divided by 0.075. And I get negative 1600. Does that answer make sense?
Yep, because that doesn't have much mass. It's got to be heck of whooping.
Yeah. So, so small mass, big velocity, big mass, smaller velocity, right? And
That's right.
it's negative because this is the negative direction. That makes sense, right?
Yep. Yes,
Oh,
it do.
There it is.
Sweet.
Okay. My mouse is over here. Okay.
Collision observation activity. No.
Oh, it worked. I scrolled it even though it wasn't on there. Okay. Okay, collision observation activity. Run many different types of collisions. What are we talking about? Let's go here. So we're going to be running many types of collisions using this ramp. And I want you guys to observe closely what happens before and after each collision.
If you were in the classroom, you'd be doing this yourself. You'd be playing with this stuff yourself.
Yes.
But let's use a big ball bearing.
Okay, here we go. All right, so I'm just going to go ahead and...
That's a collision. That's a collision.
Ooh.
Ah.
Ooh, I'm actually... that's cool.
Cool.
Okay.
Use one of the little guys and a big guy.
Like that. Okay, so here we go. I'm just gonna go... Oh, almost... Wow, that was cool. What?
You wish you were here. You could play with this stuff too.
Come on, come on, show me his boss. Okay. And then let's do these guys. Oh, you know what? Let me actually. Okay. So let me go ahead and. Ooh, stop the dead in its tracks. Okay, that one rolled with it. Okay. And now that I've raised this up a little bit, let's see how this works here. So this is different than what we've been talking about, huh?
These are not explosions.
These are not explosions because in the explosion, they both started off not moving and then they went apart, right?
Yeah.
In this, sometimes we have things that are moving at the same time.
Well, before in an explosion, the momentum before is always zero, but here, well, not always zero, but usually zero. And here we have momentum before and momentum afterwards.
Yeah. Okay, one more. Wow. That's so cool. So everything gets transferred to that. Okay. All right. So let's see. Did we see? Did you see a moving ball bounce backwards?
I think so.
Did you see a moving ball stop still?
Yeah,
How about both balls rolling off together in the same direction?
that happened.
These are all types of collisions.
And there's lots of different other things that happen, but we're not going to go through all of them.
There's a lot. Okay, so the conservation of momentum, collisions. Again, before we were talking about explosions, this is a new type of thing.
It's a new example, but it's same law of conservation of momentum.
Same law, new example. Was it same phone, same number? Ignore me. The kids say it these days. Okay. Okay. Collisions. Momentum is the same before and after. So just like oh, actually not like before, but the momentum before is going to equal the momentum after. This is just the conservation of momentum.
Yeah, and before with an explosion, the momentum before was zero. This is not zero.
I keep doing things on my computer over there. Okay, so another attention span training. We'll go to page 207.
That's chapter 9.
Chapter 9. 207. And I want you guys to read from Two Particle Collisions on page 207. Read all the way down through here.
Lots of pictures. Look at that picture.
So pretty. And then over here, we'll stop right here.
All right.
Okay, go ahead and read it.
And we'll get back with you.
All right. Now that you have read, actually, I'll leave that open. Now that you have read the reading, let's go ahead and do a practice question together. So a 227 kilogram car going 28 meters per second skids on ice and collides with another car that's 875 kilograms that's not moving. The bumpers stick together and they move off together. How fast?
How fast?
How fast do they move off together?
Should we start with a diagram?
We should definitely start with a diagram. Oh, I could have probably left that before and after. Okay. Okay, so before.
Got a big car moving and a little car sitting there.
Is that accurate?
Let's
Okay.
put wheels on it.
Oh yeah, the wheels on the bus. Okay. Okay, so we have our mass here was
2275. 2275.
Kilograms.
Yeah.
And how do you differentiate your masses? Should we call it 1 and 2, or do we just you know?
Big and little.
Big,
B and L.
ooh, big, little. As you can see, it doesn't really matter.
The mass of little is 875.
75 kilograms. Probably not that. Whatever. And then this one's not moving, right?
Velocity is 0. And the other one is 28 meters per second.
Velocity of the big is 28 meters per second. Okay, so this is before, and then after, it says what, they stick together?
The bumpers stick together and they move off together.
Dang. All right, so that means that their masses are combined, right?
Yep. Mass is big plus the mass is little.
Okay.
No,
Can you do it in your head?
well, no, go ahead.
Okay. 2275 plus 875.
Yep.
My writing needs to improve. Okay, room for improvement. This many, 3,100.
And we want to know what the final velocity of both of them is. The velocity afterwards of
Do I go like, let's go like that?
B
No.
plus C.
Yeah. Big plus little, like that, right?
Yeah. Okay, so now it's pyramid time.
Woohoo! Pyramid time. Okay, so we know that the momentum before is going to equal the momentum after, always.
Yep.
Momentum is conserved. Now the momentum before, as you guys saw in the book, we just do, no, we have A and B, they have A and B here, but we're talking big plus little.
Yep.
Okay, it's going to equal big plus little. So it's going to be
No, just
sorry, P. Jumping too far ahead, you don't do what I was about to do.
P big plus P
The
little.
momentum of, big plus the momentum of little equals the momentum of big after
Yeah.
plus the momentum of little after.
Yeah.
That's an L. Okay, so where's our answer gonna, oh, actually, you know what? Can't we combine these two?
They combine, so it's going to be B plus L.
You guys see that? Because the momentum over here,
Because
it's gonna
they're
be
stuck
traveling as
together.
well.
Their masses add together.
Yeah, so, where is my answer gonna lie?
Right here.
It's gonna lie over here. Okay, so I'm gonna break this down a little bit further now. What's our thing for momentum?
Well, what you can do makes it
Oh.
easy is the momentum of the little one is 0, so you don't
that's
have to do it.
right. Super important. This goes away, right? Has a 0 momentum. So
That
now,
way it's less stuff to write down.
less stuff is more better.
Well, you don't have to write that over again. You're going to run out of room.
Yeah, I am. Okay, you guys can keep that written down.
Yeah.
Okay, so now I can break this down into its little pieces. So this is mass times velocity, the mass of B times velocity of B, which is going to equal the mass
B
of
plus
B plus L times the velocity
Afterwards.
of B, L.
Afterwards.
After, should I put after?
No, put a little prime there.
Oh,
No, the mass stays the same. Right. There you go. All right.
Mass is the same.
Sweet.
okay. So,
What are we solving for?
what are we solving for? Yeah, we're solving for this, right?
How fast they're going off together.
So I gotta divide by the mass.
B plus L.
Divide by the mass of B plus L. Those cancel. Okay.
Why don't you put the numbers over here on the right side?
Oh yeah,
this
that'll
time?
look cuter. I mean, look more better. Okay.
Mo better.
Mo better. Okay.
Mo room too.
So the mass of B. This is
2275
why the sketch is so helpful.
kilograms.
Okay. Times the velocity of B, which is 28 meters per second. Okay. All divided by the mass of B plus L, which
Which you've
we
already
calculated.
done. 3150.
Kilograms. Okay. Then we can do it. Okay, 2275 times 28 divided by my answer from the previous one. And I'm going to get 20.22. I'll just call it 20
And that makes sense. They're going to be going slower
meters per second.
than it was before. So 20 meters per second.
Yeah, okay. Yeah, and they're going slower here, like you said. They're going slower.
Because the momentum that was all in this one now is shared between the two of them.
Mm-hmm. Where's my thing? There it is. Okay. What would be different if the little car was moving in the same direction at 16 meters per second?
What would we have to change over here?
So that means that this would be 16, right?
Yep.
Okay. So should we just erase and backtrack here?
Well, I wouldn't erase anything other. I'd change the velocity right there into 16.
Which means
And
that...
then that's gonna, that has momentum. And so
Okay.
you can erase everything down below because you're gonna have
Yeah.
to do that again.
So everything stays the same except for now we have to factor in that that car is moving. Okay, so this is the momentum of the little guy. So again, so we've got the mass of B times the velocity of B, plus now we have the mass of the little times the velocity of the little, which is going to equal Just
Mass
the
plus mass of big plus little.
That's the big plus little times the velocity prime of big plus little.
There you go.
Okay, and again, what are we solving for here?
Yep, same thing as before.
Plus little, bada boom. Okay, let's plug in our stuff here.
Now, while she's working on this, notice how messy this is. This is why it's so important to make a diagram and then do the pyramid. Start with the momentum before is momentum afterwards. What has momentum before? What has momentum afterwards?
Look how many times I'm referring to my diagram.
There you go. Or you can just refer back and forth to, whoops, it's not there anymore. That's a good thing you've got a diagram. Divided by 3150. The total mass. Okay, now you're going to have to get your parentheses going.
Beep, 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 beep. Where will we put parentheses on the calculator, Boykin?
Well, around the multiplication on the top.
Here and here?
That, yeah, and the other multiplication on the top. And you probably, since you're going to add those together, you should probably do brackets around the top, the total top. There you go.
We want to make sure the top gets done first.
Yeah.
So let's do this. So 2275 times 28, close parenthesis. I did two parentheses in the beginning.
That's a good thing.
Yeah. So, and then I just do plus,
New
875. Yeah, oh, sorry, new parenthesis, 875 times 16, close parentheses, and top parentheses, divide by 3150. And so we get 24.7.
Oh.
And you can see it's really important that you check to make sure your answer makes sense. Because you could really easily, we're talking about velocity here, you could really easily mess up on your plug and chug part right here.
Yeah, and that makes sense.
Yeah, so before our answer was, I believe, about 20.2 meters per second. And now...
and so it's slower than the big truck was going, but it's faster than the little car was going.
Mm-hmm.
So that's a good answer.
Okay. So, elastic collision. So an elastic collision, in an elastic collision, kinetic energy is the same before and after.
Yeah.
So do we have a...
We'll just give this to him now.
In inelastic, so write this down. Definitions.
Yeah.
Okay, an inelastic collision, some kinetic energy is changed into heat, sound, etc. So we lose some kinetic energy.
Yeah. Some of the energy is transported into other forms. Almost all collisions are there's perfectly elastic collisions hardly ever happen.
Yeah, these hardly ever happen.
But they're cool to work with.
Yeah, and I think what will happen, Boykin, is you would tell them it was
yes.
elastic or inelastic or whatever. But so this is what happens in the real world.
Yeah.
Okay.
If the two things stick together, that is an inelastic collision.
Mm-hmm. Oh, and I'll label that for you guys. So when they stick together,
that's inelastic.
This is inelastic. And if they were to collide and then go apart,
yeah,
that is elastic.
With the stuff we were doing, playing around with the ball bearings and the thing, we got closer to elastic collisions, but in the real world, there's always friction and heat and air resistance.
And you could hear the sound that the balls make, right?
Good point. Excellent point.
So inelastic, they stick together. Inelastic, no, they would be just separate.
Right.
Okay. Here we go. And so those are some definitions for you. Your homework is page 210, numbers 7 through 10.
Now here's the thing, give these things a shot. Mm-hmm. There might be one or two that you get stumped on, but give them a shot, and then when you get into class, we'll figure it out how to do them.
Yeah, and the most important part is start here. Well,
use
actually,
the pyramid.
start here.
Make the diagram.
Then use the pyramid.
Make the pyramid.
Yeah, and if you mess up over here, at least you understand foundationally what you're supposed to be doing.
That's very important.
Okay.
All right. Sweet.
210, 7 through 10. You